I had over 120 questions from the feedback, so thank you for that. A good portion of those were not very specific, so I removed them from the list of feedback questions, but there were a few questions that were repeated, so that's a good thing. I'll talk about that today with interpolation and regression. If the answer sheet does not answer any of your specific questions, please come to my office or send me a message over Canvas. There were some questions that were all vague. I couldn't answer them, or too broad that I would have had spent like 10 pages to answer the question. So it's just easier to have the discussion in person. But I also presume and I also expect that you prepare for the exam and you prepare before you ask the question. Because 99% of the cases, I have the answer on the slides. It's usually in a box under definition. It's usually on slide 95 or slide 76 on one of the slides. So I expect you to please try to at least look at the slides. A lot of the questions were actually like, what is linear regression? That was like on slide actually 95 under like a box in definition, right? So if the question means something else, then you have to phrase it differently or come to me and we'll talk about it, okay? I already posted this study guide or guideline for exam 2. It's the same as the previous exam 1, closed books, closed notes, closed phones, no chatting, etc. You're allowed a double-sided, letter-sized cheat sheet that you can use. I'll give you complex equations, like I'll give you the R-squared formula if you need you to calculate one, right? But if you're in doubt, write it down on your note sheet. If you feel like there's a formula that you really you're worried about me not giving it to you, just write it down and don't worry about that. The difference now is that this exam is going to have a single attempt, okay, so that we kind of square out the essay questions from attempt 1 to attempt 2 that felt a little bit unjust. So we'll do a single attempt, give ample time. It's going to be only on interpolation and regression, okay? So let's see what the expectation is. And again, please note that anything discussed in class, like our class discussions, comments made in class that might not necessarily have made it to the slides. I do my best to put everything on the slides, but sometimes there's something that shows up in the class and I talk about it in person. That's fair game. Anything discussed in class is fair game on the exam, okay? All right. For interpolation, this is what I expect from you. You are not responsible for 2D interpolation, okay? I'm going to start with that because many of the questions on the feedback form ask about 2D interpolation, and I know I had it as one of the objectives in that chapter. Unfortunately, we couldn't spend time on deriving it by hand, but we did show how you can use it in Python. So at least you got that for future courses. There was also a question on the feedback sheet that asked, when do we have to use 2D interpolation? I gave a very nice example there. So take a look at that. But you're not responsible for 2D interpolation on the exam. Okay, so don't worry about that. Okay. Given n data points, you're expected to list the highest order polynomial that fits the entire data set, list the unknowns, what you're solving for, show the conditions required to compute all the unknowns, derive the formula for linear and polynomial interpolants. So in other words, derive the governing equations. Let me clarify that, actually. Derive the governing equations for the coefficients of linear and polynomial interpolants. Given a set of data points, you should be able to obtain the governing equations for the coefficients of an arbitrary polynomial of an arbitrary order. You should be able to show how the system of equations is obtained and show the result matrix form, the result in matrix form of the linear system of equations, okay? Sorry, the resulting matrix form of the linear system of equations. List the conditions for cubic spline interpolants, all the conditions, and show how many unknowns there are and what the constraints are, and be able to list all of those constraints. So I'm going to review the spline discussion in a minute, because that was a common question that I saw on the feedback, and there was a lot of confusion about splines, and you're welcome to ask questions as we start the discussion. But you're expected to know what the conditions for the splines are, what they do, how they fit between the data points. There was an example in the slides where we had 4 data points and 3 splines in between them, listing all of those conditions. You should be able to do all of that. Okay? So because yes?
I was just going to say, for the exam, do we get a one-note sheet front and back?
Yeah. Okay? So, those conditions might be useful to be put on your sheet, okay? Calculate by hand an interpolated value using a linear interpolant. Identify which points are best used with a linear and quadratic interpolant. So I'll give, that was also a common question, and I'll address that in a minute. Essentially, you always need to bracket where you want to interpolate. So pick the point to the left and the point to the right, okay? If linear interpolation, you only need those 2 points, right? Because the linear interpolant has 2 unknowns. If you're going for a quadratic, you have 3 unknowns, so you need 3 points. Pick the point to the left and to the right of where you want to interpolate. And the third point, you pick it closest on either side. Doesn't matter, okay? But it has to be the closest to the point in question, to where you want to interpolate, okay? I'll give a specific example once we're done with this. Then given an interpolant with arbitrary basis functions, derive the governing equations for the coefficients for interpolation purposes. So again, not only just polynomials, okay? So we could have an interpolant with an arbitrary basis functions, right? And you should be able to derive the governing equations for the coefficients, okay? Regression. Given a set of observations, compute a best fit curve model that minimizes the error between the model and the observations. So that's kind of very, very generic. Clearly, I don't expect you to be able to derive the answer for like a non-straight line fit, because with the straight line, we had the answer in the slides, right? That was probably just the only case where we could get like an exact solution that is easy to just implement by hand. But the idea here is be able to derive the conditions. So to be more specific, given a set of observations, derive the conditions given a set of observations and a model curve. So that was also one of the questions on the feedback. Derive the conditions for the best fit coefficients in the model that minimize the error between the model and the observation. So some of the questions in the feedback were, where did that model curve come from, right? It came from you looking at the data. Look at the data, they look like a straight line. You're like, yeah, maybe a straight line might fit the data. There is no generating principle for that model curve, okay? I didn't show you how that model curve came up because it didn't come from anywhere. It just came from looking at the data and making a best guess. Okay, now, how does that best come? It's going to improve over time. As you do more regression, as you see more data, as you learn more about your engineering practice, you'll realize that reaction rates are always exponential in nature, okay? Bacterial growth and decay rates, they always go in the form like in the homework, 1 over c squared, for example, okay? 1 over some coefficient over the concentration squared. So you will get to know those, and then you'll be able to make a best guess model curve. But in the end, it's up to you to do the model curve. Now, in this course, I'm not teaching you to develop model curves because this is not a physics course, right? This is not teaching you the physics in engineering. So we have to employ some of the model curves that are commonly used. Clearly, a straight line is one of the easiest ones, right? You see some data, it looks like it goes in a linear trend. You say, I'm going to fit a straight line there, and that's it, right? But otherwise, there's no guiding or mysterious principle. It's literally experience and intuition, okay? That's why it helps to see a lot of math, because when you see a lot of functions, you'll start thinking, well, you know, I could combine a cosine and a logarithm, or a cosine and an exponential, and I can have like an exponentially oscillating decay, etc. That's how they're built, okay? But there's no guiding principle for those model curves. They are not obtained from solving a differential equation, for example. Define linear regression, define nonlinear regression, identify which models will result in linear or nonlinear regression, conduct linear regression for models with arbitrary basis functions. Again, that means derive the normal equations, okay, using the approach with the sum of the squares or the one with the regression matrix. You should be able to do both of these. So if I give you a model, a model for regression, and assuming n data points, and then I ask you derive the normal equations using the sum of the squares and taking the derivative, you should be able to do that, or using the regression matrix A, okay? Now, the regression matrix A only works for linear regression models, all right? So for nonlinear models, you are stuck with having to differentiate the sum of the squares, okay? Define the normal equations. What are the normal equations? They are the equations that govern the parameters of a regression model, whether linear or nonlinear. Those normal equations can be linear or nonlinear. What do I mean by govern? Govern the parameters of the model. It means if you solve those equations, the answer to those equations are the parameters of that model curve, and such that those parameters minimize the error between the model and the data. That's what I mean. The governing equations of the parameters are the normal equations, okay? Just like when we say the governing equations of temperature, the governing equation of temperature. It's the equation such that if you solve that equation, you get the temperature. If you solve the normal equations, you get the parameters. You get the parameters that minimize for the model, minimize the error between the data and the model. Derive the governing, so in other words, normal equations for nonlinear regression. Derive the governing equations for nonlinear regression. So in other words, the normal equations for nonlinear regression, define and compute the mean, standard deviation, and standard error. Define and compute the R-squared value. Linearize some nonlinear regression models. There were 2 or 3. And formulate and derive the normal equations for nonlinear regression. That's the same one as this one. So I'm just going to delete this one. Okay? All right. So I have a long list of questions and answers. I'm still working on a few. I think I answered all of them, but I'll show you how many questions we've had this year. So this was the questions on interpolation. I literally spent all morning on both of these sets. So this is the example that I just mentioned about 2D interpolation, but you're not responsible for 2D interpolation for the exam, so that's for your own benefit and knowledge. So there's a lot of questions, all right? So this was, I think we had 60 questions. I boiled it down to 44. There's a lot of useful questions over here. Now, the common theme that I observed, left. This doc always is messed up. Okay, so let's see. I have some answers for the common questions that I observed. Okay. Oops. Okay. All right. So those 3 questions were common for the interpolation discussion. The behavior of high-order polynomial interpolants. There were 3 common questions. What are the best points for doing local, quadratic, cubic, or linear interpolation? Question about cubic splines and the oscillatory behavior of high-order polynomial interpolants. Okay, so let's talk about all 3. Okay, so what I'm showing here is an example data of density versus temperature. So we have some measurements for temperature at 120 Celsius, 135, 210, 227, 287. You see on purpose they're not equally spaced, okay? And then we have values for the density, 2.96, 2.61, etc. And they're plotted over here. And notice the x-axis has the temperature, the y-axis has the density, and I put the values that we obtained experimentally on these red dots up there, okay, with the value for the density. Now, you're asked to find the density at 198 kelvins, okay? Using, yes?
Are these slides on?
Not yet. I literally just built them before coming here, so they're not yet there, okay? So with a linear interpolant, with any interpolant, you always choose the point to the left and the point to the right, okay? So I would choose for a linear interpolant these 2 points. That's all you need for a linear interpolant, okay? Now for a quadratic interpolant, you need 3 points, right? So you would use the point to the left and the point to the right, but also you need one more point. Which one would you choose? Makes sense to choose this point because it's closest to 198, okay? So I would choose, which one was this one, 1.566, 227, okay? So I would choose 135, 210, and 227. Now, it's not wrong to choose 120, this point, but it's going to bias the data more towards the left and away from your intended interpolation point, okay? You want to stay as close as possible to where you're interpolating, okay? For a cubic, you need 4 points. So we got the point to the left, the point to the right. This is our third point. The fourth point could be on either side, but it needs to be the closest. Which one is the closest? Turns out that this point is going to be the closest. How do I know? Take the difference, 198 minus 120, and 198 minus whatever, 287, okay? This point is closer to 198 compared to that point, so I would use these 4 points to do the interpolation, okay? Now, these are local interpolants, right? So if you want to interpolate the full data set, you have to build a very high order interpolant, which is a very bad idea, okay? So the other option would be to stick to maximum a local cubic, okay? Which brings me to the question of why high order polynomials become oscillatory at endpoints. The proof is very complicated, okay? It's very complicated, but if you want to read up about it, the phenomenon is called Runga's phenomenon, okay? He discovered it and pointed it out, and specifically this happens not because the polynomial is just high order, it's because the points are equally spaced. So one way to fix that is to make the points unequally spaced, but they have to be like Chebyshev points. And what are Chebyshev points? Well, I don't want to spend time teaching that in this class. So don't use high order interpolants. Nobody uses them. We know the fix, but they're almost always useless, okay? The solution for those coefficients is very stiff, very complicated. Don't do that. Instead, we always do local, linear, quadratic, or cubic, okay? The easiest thing is to do a local linear interpolant, and with Python, you have your function interp. It just returns to you one full function for the entire data set. So you don't have to say, oh, where does my point fall between those 2 points, and go find it and do the linear interpolation. With interp, you get that whole thing, you're done. The problem then is with quadratic and cubic local interpolation, there's no built-in Python function that does that for you for the entire data set. So what you would have to do, you'd have to go and say, okay, where am I interpolating? Find the closest 3 points or 4 points, like we did in the previous slide, and then do the interpolation. And that's very annoying to do. Okay, you can write a function for that and do it. That's fine. Okay, but almost all languages, almost all programming languages, they provide an alternative, which is cubic splines. Now, what are cubic splines? They are still local cubic interpolants. Okay. There's no different. A cubic spline is a polynomial interpolant. There's no mystery about it. It's still a polynomial interpolant. It's just created differently. With a standard cubic interpolant, you have to pass it through 4 points. But with cubic splines, we want to pass it with only 2 points. So we need 2 more conditions, right? Because it has 4 unknown parameters. The cubic interpolant, A0 plus A1x plus A2x squared plus A3x cubed, right, has 4 unknowns. So that's why we need 4 points. Or, in other words, you could say I need 4 conditions. So with cubic splines, we say we just want to put a cubic between 2 points, but let's create more more conditions to be able to find all the parameters, right? So these were the slides that we discussed in class. The idea is, and this is just one example, is between each pair of points, you want to put a cubic. And like I said, passing the cubic between 2 pair of points only gives you 2 conditions. We still need 2 more conditions per spline. With 4 points, you can put 3 splines over here. So let's write those down. First spline is A1x cubed plus B1x squared plus C1x. Second spline, it has different coefficients. It's A2x cubed plus B2x squared plus C2x plus D2, right? And so on, okay? So the conditions in general, for n plus 1 points, we can build n splines. 4 points, we can build 3 splines. 5 points, we can build 4 splines, and so on. Now, for each spline, we need 4 variables. Why? We need 4 conditions. Why? Because the spline is a cubic, and a cubic has 4 coefficients. So you need 4 equations for those 4 unknowns, right? The coefficients are the unknowns for the spline. So you need 4 equations for those 4 unknowns, okay? Therefore, we need 4n equations, 4 times n conditions, okay? N is the number of splines, 4 conditions per spline, so we need 4n. Okay, so how do we do this? These are the conditions listed here. At each data point, for the interior points, the values of adjacent splines must be the same, okay? So the value of this first spline at x2 needs to be equal to the value of this spline also at x2, and same thing here. The green spline at x3 needs to be equal to the value of the purple spline at x3, okay? Now this gives you 2n minus 1 conditions, all right? So that means we're just past, that's equivalent to what we did with standard interpolation. We just passed the interpolants through the data point, okay? Now, at each point, we want to also match the derivatives. So those are the additional conditions that are non-standard for what we did throughout interpolation. Throughout interpolation, all we did was pass the polynomial or the interpolant through the points. Here, we're passing through the point, but we're also matching the first derivative at the interior point. So the derivative of this red spline over here is equal to the derivative of that spline over here. Can we match the derivative? Absolutely, because the derivative of a cubic is very easy to calculate. So you just differentiate. That's 3a1x squared plus 2b1x plus c1 evaluated at this point is equal to the derivative of the green spline, which is 3a2x squared plus 2b2x plus c2 evaluated at that point. Okay? That's it. So you match the first derivative, but you also match the second derivative. That's why splines are so successful, and they provide very smooth interpolants, because you're matching the value, the first derivative, and the second derivative. Okay? It's very nice, continuous, and smooth. Okay? So same thing here. For n minus 1 points, you have n minus 1 constraints. Okay? We still need 4 conditions. The first and the last splines must pass through the first and the last point. So we did everything so far on the interior points. We still have the first and the last points. We passed the first spline and the last spline, so that gives us 2 constraints. We still need 2 more. Well, we say we match the curvature, or we specify the curvature at the end points. Oftentimes, we just set that equal to 0. We set the second derivative equal to 0, at the first and the last point. You don't set the first derivative to 0 because it's going to force the spline to go flat. We don't want it to go flat, so we cheat and we say we're going to match the second derivative. Okay? Okay, then I give you this example. Okay? 4 points, 3 splines, 4 unknowns per spline, so you need 12 constraints. and then you match, you list all of those constraints. The first 6 conditions are matching the points, okay? F1, the first spline at point x1 is equal to y1, that's given to you. And then F1 at x2 equal y2. F2 at x2 is equal to y2. F2 at x3 equal y3. F2 at x3, F3 at x3 is y3, and F3 at x4 equal y4. That's just passing the splines, okay, through all the points. Now for the derivatives, f'1 at x2 is f'2 at x2. That's easy. How do you evaluate that? You have f1, you have f2, you differentiate, you evaluate at x2, you set them equal, that gives you an equation. Same thing for f2 prime and f3 prime. And then the second derivatives on the interior points and the second derivatives at the end points. Yes?
So I understand how each of the points, like on the differentiated functions, make it go through each point. And then the first derivative makes sure that each cubic spline is like tangent, so it's smooth. What do we get out of having the second derivative?
Also smoothness. Yeah, so smoothness up to second order. That's how we say it, right? So it's continuously differentiable and continuous up to second order. So there's no fracture up to the second derivative. At the third derivative, you might become piecewise continuous, okay, or might become fully discontinuous, okay? But there's no guarantees there, okay? But there's still smoothness, first, second, third, whatever. You say the function is smooth up to the second derivative. Okay. Yeah. Okay. Now, for regression analysis, actually, if you have a question, you can ask it now, or feel free to interrupt. If there's something, I know it's been a while we did interpolation. Yeah, yeah. Now these slides are taken. These last slides are taken from the interpolation slides. Okay. Yeah, they're the same. There's nothing new here. Okay. Okay. Now, these guys, when you expand the derivatives, right, you'll just have a system of linear equations for the coefficients. You solve that system of linear equations, you get. What do you get? A1, B1, C1, D1, A2, B2, C2, D2, A3, B3, C3, D3. You get all of those, okay? So then you have the formulas for all your splines, okay? In Python, you call the cubic spline, you tell it, I want to interpolate, let's say, at some point in that green spline. It will automatically figure out which spline it needs to use, and then applies the interpolation using F2, for example, or F3, okay? All right. So now let's go to regression. Okay, with regression, we also had, I think I finished answering all the questions. But there were things that worried me a little bit. Maybe some of you missed the lectures or did not study the lecture before putting the feedback. But please make sure if you're like iffy on the basic concepts, like either come talk to me and study the slides, re-listen to the lectures. There are questions that reflect that the material was not properly understood by whoever asked the question. So please, please, please make sure that you can master this. Regression is a very important topic, okay, as you move on in your life and career, okay? I personally did not study regression. I was never exposed to regression analysis until, after my PhD, frankly, okay? And then I was like, wow, this is so amazing, okay? That's why I love to teach it, because I learned it by myself, right? And then when you learn by yourself, you create, you fill in the gaps as needed and you understand the material better. But the question on does linear regression mean regression to a straight line? No, it does not mean that, at least not in this class, okay? And that was clarified in the slides as well, okay? So be careful, do not make that mistake in the exam, okay? In other courses, I don't know what the standard they're gonna set, but I always say regression to a straight line, regression to a quadratic, regression to this model, okay? Linear regression, we mean that the normal equations are linear, okay? This question was actually a very nice question because it does answer a few others as well. So let me read it, and then I'll go to some slides. Okay. Why is there a need for standard deviation? I understand that the difference between standard deviation and standard error quantifies the improvement of the regression. But if our goal is to find the least difference between the regression line and the data points, shouldn't standard error alone be enough to know how fit the regression line is? It is a fantastic question, okay? So this is an example of a very specific question that I want in the feedback, right? So that I can answer it and we can have a discussion about it. You're not wrong. So the person who asked the question is saying, well, why do we need the standard deviation when we are assessing the fit of a regression curve? If you remember, we computed the standard deviation when we were looking at just standard data, and then we computed the standard error for the regression curve, which was the equivalent of the standard deviation, okay, but for a regression curve. How far is this data spread around the regression curve, okay? Unfortunately, in and of itself, the standard error it just gives you a value. It doesn't tell you how good the fit is. So if you take the femur and height data, the standard error was 1.73. I can't say anything about that. I don't know. What if you had data that was order 100 and your standard error was 227? That doesn't tell you anything. Why? Because it's not normalized, or in other words, it's not measured relative to something else. Okay. So the best thing that we can compare the standard error to, one of the best things, not the only thing, but one of the best things is the standard deviation. Why? The argument is that the standard deviation is sort of the error in the data with respect to using the mean to represent the data. Okay? So if we use the mean to represent the data, you have standard deviation. Then you use regression to represent the data, you have standard error. Then you compare the standard error to the standard deviation. That tells you if regression has improved your representation of the data over just using the mean. Okay? This is one of the best ways that's why we need that standard deviation, is to allow us to compare the standard error to something, right? Because standard error in and of itself is really not very meaningful. It just tells you this is how much the data is spread around the curve. But it doesn't tell you, is the curve good enough? Now, you might say, well, isn't that the same case for standard deviation? Standard deviation is just a number. No, because standard deviation is not trying to assess the fitness of something. Standard deviation is a property of the data. You're given data, this is the mean, this is how far it's spread. That's it, okay? It's just a property of the data. But the standard error and the regression line, we are holding that to a higher standard. We're saying, is my regression going to be a better representation of the data? Okay? So then that standard error associated with the regression curve needs to be compared to something. Okay? It needs to be measured relative to something. Then we measure it with respect to the standard deviation and normalize it, and then you get a value between 0 and 1, which is the R squared. Okay? And the R squared value is like, you can be talking about apples and oranges or populations or heights or GPAs or temperatures. It's a common language. We say, oh, my R squared regression is 90%. You could tell, you don't have to know anything about the problem, whether it's bones or GPAs or oranges. 90% R squared value is a good regression. Okay? So it standardizes that discussion. All right? It's a great question. Okay. Let me go to some of the slides, and then you can spend time looking at these questions as you prepare for the course, for the exam. Okay. One of the great questions is, why do we set the derivatives of s to 0, and why does that produce an, does that, okay. And why does that, okay. So the first part of the question, I expect you to know this from calculus, okay. When does a function have a minimum or a maximum? It's when its first derivative is equal to 0, okay. All right. That also applies to 2D, 3D, and any n-dimensional function. Any multivariable function has a minimum or a maximum, has an extremum, okay, when all the first derivatives with respect to all the independent variables are equal to 0, okay. Now the kicker is, why does setting that equal to 0 always result in a minimum? What guarantees a minimum? So we wrote the sum of the squares of the errors, right? And we differentiated, so that S, which is equal sum of yi minus model squared, then that's a function. You can plot that with respect to your parameters. You can plot it and see it in 3D, okay? But then why does taking the derivatives and setting them equal to 0 always produce a minimum? Why wouldn't it produce a maximum? Okay? Well, at least for linear regression, that sum of the squares is always a hyperparaboloid, or a parabola in n dimensions. In one dimension, you have just one parabola. In two dimensions, where you have two model parameters, you get a paraboloid. And when you have a model with 3 or 4 parameters, or n parameters, it becomes a hyperdimensional paraboloid. And for a paraboloid, just like a parabola, a hyperdimensional paraboloid always has one minimum, always. And it occurs where all the derivatives are equal to 0. So take this example with the straight line. This is the sum of the squares. You have yi given data minus a xi, sorry, typo here, plus b squared. You're trying to find a and b. Now, when you expand this, you're going to get a squared and b squared, okay? And that's a paraboloid in 3 dimensions. When you go to more parameters, you're going to get a squared and b squared and c squared and d squared, etc. All of those will create always, for linear regression, always, you're going to get a hyperdimensional paraboloid. And for that, you only need to find the first derivatives, set them equal to 0, and you'll hit this point, okay? Now, this is not necessarily true for nonlinear regression. That's why we prefer linear regression. Remember, in the last lecture, one of the previous lectures, I said I always prefer linear regression because you're always guaranteed an answer. With nonlinear regression, we were struggling finding the initial guesses and even if it converges or not. With a nonlinear sum of the squares and the conditions for that, you might be hitting a local minimum or you might be hitting a local maximum. There's no guarantee. There's no guarantee there's even a global minimum. That's why we always prefer linear regression. If you can linearize the model, always linearize it and solve the linear problem. Okay? In terms of accuracy, that's a different story, but if you can linearize it, always linearize it. If you can represent your data with a linear model, always represent it with a linear model. Okay. Now, the other questions, I don't have slides for them, but I can answer them verbally. The normal equations, they are see slide, I think, 95 on regression. Okay, they are, no, that's for linear regression. They are the equations, it's on some other slide. The normal equations are the equations that govern the parameters of a regression model. The normal equations are the equations that govern the parameters of the regression model. What do I mean by govern? They are the equations such that if you solve them, they give you their answer as the parameters of that regression model. Okay? If you solve these equations, you get the parameters, and then because those equations minimize the error, you plug the parameters in the model, that model is going to minimize the error, the sum of the square of the errors. Okay? When to use linear versus nonlinear regression, I kind of just answered that. Always prefer to use a linearized version or linear regression, but in general, if your data does not fit a linear model, then do a nonlinear model. That's fine. What's more important about worrying whether linear or nonlinear, what's more important is to capture the data well. And then we'll figure out how to solve the nonlinear equations somehow, okay? But more importantly, you have to find a good model that represents your data. If it happens to be nonlinear, so be it, okay? That's your job as an engineer, right? I cannot give you guidelines, when there's this and that. I don't know. I don't know what data you're going to be looking at, okay? So that comes with your judgment as an engineer, and that's why people are going to rely on you. Yeah?
For the model and the homework, where they take that they're reciprocal,
Yeah.
did you just know that from experience, or there's ways you can tell when it's going to end up being?
If you look at the last slide in the regression, so that's in biology, it's very common they do that. Yeah, so I learned that from the biology experts, right? But it comes with experience, right? And then you start picking up tricks. That's why you study math, right? Why do you study math? Even if there's no hope of applying it anywhere on Earth, what you're applying abstraction in your mind. You're building a Bayesian, a set of experiences that you can use, a set of tools and ways of thinking that you can use for problems you haven't encountered yet, okay? That's why you study math, okay? All right, when to use linear nonlinear? Okay, phi and psi, etc. in the regression matrix. So those are generic names of basis functions, okay? They're just generic names. Phi and psi are just random, whatever function. They could be sine, cosine, log, exponential. They're just placeholders for some arbitrary basis function. I don't want to use f and g because we used f for the regression curve model, right? And g is gravity, right? So phi and psi, they're like, nobody has used those yet in the course, so we'll use them as placeholders for basis functions. That's all there is, okay? All right? So I'll put those up on the front page in Canvas. So there's already a section for exam 2. I'll update the study guide, put the other slides on. Ethan?
Integration, is that going to be on the
No, that's going to be on the final. Yeah, only interpolation and regression, okay? Yeah.
When we're trying to find values in between data points or whatever, what would be best to use? Would it be best to use interpolation or regression?
Well, okay, so that's a good question too, and I answered that that's actually a good question. So it depends. Some data come from precise physical laws, like Newton's law, right, or the ideal gas law. You go and measure temperature and density. You measure it here. You measure it, in Alabama. You measure it, whatever. It's going to be the same thing, right? It's not influenced by environmental factors or things that are out of your control, right? Temperature and density behave the same way, even in outer space, right? And so in those cases, the data is nice and structured, okay? So I would use interpolation in those cases, reaction rates, things like that. Now, for things that are influenced by thousands of parameters, like person's height versus femur length, right? So it's clearly a person's height and femur length are correlated, but there's so many things going on. There's genetics, there's nutrition, there's the environment you're living in, and all of those things, family history, and all of that, right? And you see the data is scattered. You see for the same femur length, you might have two heights, right? So in that case, you use regression for these inexact physical laws, for those statistically relevant data, per se, right? Where you really, you can't just have one set of points. Like if that's the case, that's like just a huge discovery, right? But in most cases, you're observing something that's affected by thousands of parameters. You're correlating with a single other variable. You're going to get like a little scatter, then use regression there, because you're not capturing. You don't have the exact. You don't have the exact data anyway. You're just capturing a trend. Okay, does that make sense? Yeah, that's a good question. That's a general question, essentially. Actually, it might be a good question for the exam. But yeah, in general, so when the data is comes from an exact physical law, use interpolation. When there's more kind of a scientific observation of something, use regression. Yeah. let's get started on the last unit of this course. I can't believe we're there. This is a very fun topic to teach. There's endless opportunities to do things with differential equations. So we're just barely touching the tip of the iceberg in this course, but I hope it will set you up for a lifelong of curiosity and learning, because differential equations are the cream of the top of the cherry of the icing of the cake of scientific accomplishments. There's nothing better in modeling than differential equations. And differential equations have done me a lot of good in my career, as opposed to data science, but we'll get a chance to discuss that. But there's not a single data science model now that can beat the physics brought in by differential equations, okay? And I hope in this unit that I will get to revisit differential equations with you, at least at the ordinary differential equations level. So who is currently taking ODEs and who has taken ODEs? Okay. Okay. So for those of you who didn't raise their hands, have you never had an ODE class? Okay. Okay, do you plan on like taking one next year? Yeah? Okay. Oh, you did?
So linear algebra and differential equations class, they just might not realize that that's also ODEs.
Okay. Okay. So I guess you've all seen ODEs or are currently taking it. Okay, that's great. Because I hope to give you a different perspective. You probably learned it from the math people who are going to be more focused on like things like existence of solutions and analytical solutions. In this unit, I'm going to give you a different perspective on differential equations. And in fact, we're going to build, depending on time, or you are going to build, or we might build together a model for the pandemic. Now, that was very exciting during the early days of COVID, and everybody didn't know what was going on. So we built this model together here in class, and different students started coming up with their own different models to track like social distancing, masking, hospitalizations, etc. It was quite interesting in seeing kind of the effects of. We discovered that there was like a threshold point where shutdowns become ineffective, right? Where you're like shutting down everything, then we try to add cost to that. Anyway, that's the stuff you could do with differential equations, okay? However, before we get there, we need to start with something called numerical differentiation. So that will revisit a topic we touched upon earlier when we did the heat transfer problem. It's just one lecture, but I need that discussion so that we have all the tools that we need to do differential equations, okay? So when you think about it now in this course, the first unit was solving algebraic equations, right? The second unit was curve fitting or data analysis. Now the third unit is solving differential equations, okay? Why did I put differential equations at the end? Because they're a little harder. Working together through regression and interpolation kind of made us better fit to do Python stuff and reuse linear solvers and nonlinear solvers. We're going to need all of that with differential equations. But first, because there was no life hack today, I'm going to give you this life hack, okay? The life hack is not to tie your horse with a chair, if you have a horse, but the life hack is that sometimes the thing that is holding you back is all in your head, okay? So from the horse's perspective, the horse is tied up, right? But it doesn't know it's tied up to a chair. It could easily just yank that chair and just keep moving, right? So put things in perspective. You know, take a larger perspective sometimes, okay? And you realize that, oh, you know, this is just all in my head, and I could perhaps get over this obstacle or hurdle. All right, numerical differentiation, and I don't know, this is the wrong semester clearly, so this is spring 2023. Okay, spring 2023. At the end of this chapter, you should be able to do the following. Define the finite difference method. We kind of know what it is a little bit. Numerically compute the first and second derivatives for discrete data and continuous functions. define and estimate the convergence rate of finite difference schemes, finally, define what is meant by order of accuracy of a given finite difference scheme, and then use the Taylor series to derive a few simple finite difference schemes. If you remember the heat transfer problem, I told you one day I will show you how we can convert that second derivative to ti plus 1 minus 2ti plus ti minus 1 over delta x squared. We're getting there. This is the step that gets us closer to that. Now, we did touch upon a little bit on the finite difference method when we did the forward difference method early when we were computing errors, right, and the truncation error, right? So we did the Taylor series and we truncated it. So we're going to revisit that and build upon that a little bit more. The motivating question, and that also comes from COVID, probably I have to replace this problem next year because this is not an issue anymore, but this plot was like early into the pandemic. This was taken in 2020. I was teaching this course, and then, you know, we reached, this is like days since the outbreak, day 0, okay, day 40. So this was like a month and almost 5 weeks into the pandemic. I showed this plot, and then the next lecture we had to go online, okay? And so this is showing the data for mainland China in blue, all right? And then, you know, as it spread out from mainland China, then the world started picking up infections in orange, right? So we have these two sets of data, total number of cases, okay, for both mainland China and the world. And then the question is, what is the rate of spread of COVID-19? How fast is it spreading worldwide, given these data? So what would you do? I gave you this data. Yeah.
My initial thought would be to calculate the rise over run for each data
Okay.
point and then take the average
Okay. Yeah. Calculate the derivative and take the average of what?
of each rise over run, like for like an average rate of change.
Or you can just do it at each point. It just gives you one value, right? And because you need it daily, right? So at the end, what we're really interested in is really at the end, like what is the rise over run? So you would do it at each point, right? You don't have to take the average over the full data set, okay? Yeah, what other ideas? Todd?
You could do something like, for the first part of the population model, where everybody gets, like, it's first exponential and then it gets to
Okay.
capacity, and you could do a different model for the orange data once it gets spread to that part of the world.
Okay. Okay, yeah, so what Todd is saying is we can fit something. We can fit a curve, whether in turbulent or like a regression, do a regression curve by building maybe early on an exponential rise, and then, you know, when we hit a plateau, which you call carrying capacity, perhaps that's more to population growth, but we're going to visit that in a few slides, well, in the next lecture. But yeah, so you would fit a model and then differentiate that model and then evaluate the derivatives, right? We're going to do the former idea. We're going to do the idea that Ethan suggested for numerical differentiation. Why? Because I need numerical differentiation to build up for differential equations, okay? So yeah, those are the two ideas primarily. We're going to use a Taylor series over here to define these derivatives. Now, the rise over run gives you the derivative locally at a point. And yeah, we all know that. But that's only one way to compute the derivatives. There are other ways that have less error in them that allow us to compute derivatives and give us better approximations. Now, the other question is, what if you wanted to calculate the second derivative, right? So it's not rise over run. You'd have to do some more algebra to figure that out, right? So we're going to use the Taylor series to build up these approximations to the derivatives. Now, remember this slide from the Taylor series. That was like early on when we talked about the error. We already defined what the Taylor series is, but a quick reminder, for any continuous function or any function that exists that gives you data, you can express that function at any point x, at an arbitrary point x, around any other point. We call it x naught over here. And this would be the formula. So the idea is that if you know everything at some other point, okay, then you can express at some point x0, you can express the function at any other point using this Taylor series. Okay? So now we're going to use that to try to compute derivatives of discrete data or continuous functions. All right? Here's the situation. Here's the setup. You have a bunch of data points discretely organized over what I'm going to call a grid over here. So on the x-axis, you have these points x1, x2, all the way to some point xi, all the way to xn endpoints. And the spacing between these points for now is fixed. The spacing is h. Okay, it's a fixed value, constant everywhere. And for each one of those points, there's a function value, f of x1, f of x2, and so on. Okay? And there's a curve that passes through all of those points. All right? So for simplicity now, I'm going to call f of xi, I'm going to call it fi. So I don't have to carry a bunch of parentheses that are annoying. So when I say fi plus 1, it means f evaluated at xi plus 1. Okay? Okay. Now I'm going to compress those over here so we can simplify what we're looking at. All you need to know is that for these coordinates, okay, or for these independent variables below x1 all the way to xn, you have a bunch of function values f1, f2, all the way to fn. Okay? Now, given these function values, the Taylor series is useful in finding the derivatives of that function, right? So in other words, your objective is to find f prime at xi for any I. So our objective is to find the slope of this function f at an arbitrary point xi. Okay? All right. Now recall the Taylor series before you do the activity. Recall the Taylor series is the Taylor series of the function f at some point x is equal the function value at some point x naught, its derivative at x naught times x minus x naught, and so on. Now I want you to write the Taylor series of f at xi plus 1 around xi. Okay? So f at xi plus 1 around xi. So your x naught is going to be xi. So go ahead and just write this down as is, first term, second term. Okay? But do it for f of xi plus 1 around point xi. This is the Taylor series of f of x around x naught. Okay? Just simple substitution. Don't lose our objective. Our objective is to get to compute f prime at xi, okay? But this is the trick to get to it. Is we first write the Taylor series of f at xi plus 1 around f of xi, okay? And see what happens. Okay? You guys have it? Yeah? Okay, what did you do? What did you do? You just replaced?
X with xi plus 1,
Uh-huh.
x naught, xi.
Same thing here. And what about this guy? You get?
I guess you get like delta x.
Or h, right? So you get xi plus 1 minus xi, which is h, right? Okay, that's right. So very simply, all you have to do is set x to be equal to xi plus 1 and x naught to be equal to xi. These are just dummy variables, okay? But when you connect them to I plus 1 and I, that gives you an anchor point that we're expressing the function f at this point using the previous point, at point xi plus 1, using information at point xi, okay? So you simply substitute x with xi plus 1 and x0 with xi. You get this. And now remember, our spacing is fixed. So xi plus 1 minus xi is equal to h. And then you simplify the nomenclature of f of xi plus 1 is fi plus 1 and fi. And you get this nice compact formula. Fi plus 1 is equal fi plus h fi prime, etc. and so on. Okay? Now this is cool because now we were able to relate, we have the function values, all of the f's everywhere, okay, that's given to us, all right? Suppose it's given to us, okay? And now we have a relation between the point at I plus 1 and the point and the value at I, but we also have a bunch of unknowns, actually, f prime I, f double prime I, and so on. Okay? So now do what we did also during the errors lecture. Solve for f prime I. So move f prime I to the left-hand side and move everything else to the right, and give me a formula for f prime I. Okay? Don't be afraid to put 3 dots, okay, etc., essentially saying. Okay? So we did this also, if you remember, early on in the error analysis chapter. And I promised you we'll come back to it, but we're going to dig a little bit deeper this time. If you solve for f prime I, so treat f prime I as your unknown. Okay? So move it to the left-hand side, divide by h, move everything to the right-hand side, divide by h. Did you get, Todd? You get something? What do you have?
Oh, you want to tell me?
Do you want to tell me?
F prime I equals
Parentheses.
f
Uh-huh.
fi plus 1/2 h squared double prime I
Okay.
dot dot dot.
Over h. Okay. That's right. You just simply solve for f prime. You just take f prime to the left-hand side and express it in terms of everything else. The way I like to write it is divide by h. Divide every term by h. Okay? So you get fi plus 1 over h minus fi over h. I'll combine them into this. And then the rest, you know, h squared, we had h squared f double prime divided by h, it becomes h f double prime, right? And the same thing for all the subsequent terms. Okay. Now this term reminds you of something. Yeah.
Would it not be minus 1/2 h double prime I?
No, because, yeah, sure. It doesn't matter, actually. It doesn't matter, but you're right. I actually cannot edit this equation right now, but you're right. Yes. Okay. There's a sign issue here. This should be a minus. Thank you for pointing that out. Okay. But it's not going to matter because that's going to be a truncation error. Okay. We're going to call it order h. Yeah, we're just going to, we don't care about the sign for it. Okay. But it is important as you're building higher order approximation. We'll see. Okay. Now this first term reminds you of what you learned in high school. Rise over run. Okay. Fi plus 1 minus fi over xi plus 1 minus xi, right? And that's indeed the definition of the derivative. Okay, now in the limit as h approaches 0, all of these terms disappear and you get the exact derivative, okay? But we're not going to do this limit because we are doing discrete mathematics. And then we can define an f prime, a way to compute f prime given only fi's by neglecting all of those terms that we don't know. We don't know f double prime, we don't know f triple prime, we don't know any of those. So why not just neglect them? And you could argue that, well, all of those derivatives are multiplied by h squared, h cubed, and as h gets smaller, those derivatives are bounded, so they don't go to infinity. As h gets smaller, all of those terms are going to go to 0. Okay? So in that case, then we can justify neglecting those terms, and then we say our approximation to the derivative, see the approximate sign, is fi plus 1 is fi over h, right? That's one way of doing it, with the error being all of the other terms. And remember, we called that the truncation error. It's taking an exact mathematical expression and chopping it, removing some pieces of it. Those pieces are called the truncation error. Now, for this method, so now what we accomplished here is given only function values, fi plus 1, fi minus 1, etc., we can compute the derivative at any point. Okay, just given the function value, we can approximate the derivative. No mystery, no magic here. The new stuff you're going to learn is about the truncation error. Now, the truncation error, again, if you go back to our definition in error analysis, is typically dominated, is always dominated by that leading order term. Okay? Because the way to think about this is that we're going to keep h, which term is smaller compared to all the other terms. As h gets smaller, this term is going to dominate. This leading term is going to dominate. So we say that the error on average behaves proportional to the leading order term, okay? Now, in this case, f double prime for a given problem, in all cases, these second and third derivatives, they're bounded, okay? If you're dealing with a physical problem, they're not going to go to infinity, right? They're bounded by a value. And that value is independent of h, of the spacing. So really, that value is a constant, okay? That value is a constant. So we say that the error is proportional to h, the spacing. Now, h, the sensitivity to h, is very important here, because that's the only parameter we can control when we are building an approximation to a function. You can use double the spacing, or you can triple the spacing, right? So what happens to the error as you change your spacing? That's why I like to express things in terms, you asked me the question, I think last week, for the integration. Why do I like to express it in terms of n? Because that number of that number of segments for the integral is what I can control. So I want to express the error in terms of that. And same here, we want to express the error in terms of the spacing h. So our truncation error is always bounded by some constant times h in this case. And then we call this order h. Now this notation, big O notation, order h, all that means is that the error scales with h. Or order h means that my error, or whatever, if you say something is order h, it means it's, yes?
What is the big O?
Big O, that's what I'm defining right now.
Just like, no, like look at
It's order. That's what it says. It's order h. Big O means order. Pardon me?
I said, how do you type it in LaTeX?
Oh, this one? MathCal, \mathcal, math calligraphy, so \mathcal, okay? But this symbol means order, and it's called the big O notation. What it means is that when I tell you something is order 10, when I say something is order 10, it means it's not 0.1, it's not 0.5, it's not 100, it's not 1,000, it's 15, 12, 23, 18, that's, okay? Order h, it means something is just proportional to h. It's not proportional to h squared, it's not proportional to h cubed, it's proportional to h, okay? And that has a very, very specific meaning, okay? So then you could say exactly now, we could write the approximation to the derivative, f prime at I is equal f at I plus 1 minus f at I over h plus order h. And look at the exact, this is exact notation, okay? Because all of those terms are, we just say they're order h. However you change things, they're only going to scale with h. They're only going to change with h, okay? Now visually, if this is the true slope, the forward difference approximation gives you the following slope. Okay? Now this is bad for this example, but I could come up with an example where the forward difference is better than any other difference, okay? But this is visually what the forward difference slope gives you. The exact true slope is the line tangent to that point at I. The forward difference is going to give you that slope over there, okay? All right, so now let's go back to this error. This is important, okay? We say that the error is order h. This means that the dominant term in the truncation error is proportional to the spacing h. Now here's the kicker. This also means that if h is cut in half, the error will also be cut in half. If you remember that first or second homework, I asked you to compute the derivative using the forward difference approximation for values of h like 10 and then 5 and then 2.5, you cut it in half. And I asked you, what do you observe? What does the error, how does the error behave? Okay? And then the answer was, that method was order h. So as you cut h in half, the error is cut in half. Okay? So let's prove this. If the error at some spacing h is equal to ch, then if you cut the spacing in half, then the error at h over 2 is c times h over 2. But ch is eh. So the error when h is cut in half is equal to the original error cut by 2. So you cut the error, if you cut h in half, you cut the error in half. Okay? I see some squints. for some spacing h, you have some error. If you cut h in half, what happens to that error? It gets divided by 2. Yeah. O is in a way a blanket nomenclature for the entire truncation error. O is not a value. It's not a value. It's not a value. I mean, you can express the entire truncation error, but O of h says that all of that term that is represented by O of h, order h, is dominated by h. And it behaves, it changes in a way that's proportional to h.
So it's kind of just there to show the rest of it.
Yeah, to hide all of that into one term, because I'm not going to carry that truncation error and the 3 dots everywhere. We're just going to call it OH, but then we know that the behavior of that term, all of those, there's an infinite number of terms there. All of those terms are going to be dominated by a constant times h. That's how the trend is going to be. Okay, and we're going to prove this when we jump on Python. Yeah. But yeah, as the bound, as the upper bound of the error. Yeah, as the upper bound for the error. Okay, so what you should take from this is the meaning that when you have a method that's order h, what it means for the error. You immediately could say a method of order h means that the error is a constant times h. Okay? All right. Now, in general, an approximation is said to be of order p if the truncation error is order h to the power p. Okay? So remember, our truncation error had h, f double prime, etc. For this case, we're going to develop methods where the truncation error is, the first term in the truncation error is h to the 4th. So that method is a 4th order method, and the truncation error is ch to the power 4, or order h to the power 4. Okay? Now, show that if a method is order h squared, then if h is cut in half, the error will be cut by a factor of 4. Okay? So write EH equals CH squared and deduce what happens to EH over 2 in terms of EH. What happens to the error? You're starting with an error at some spacing. You cut the spacing in half. What happens to that error? Just write it down. Because then it gets interesting when you have like cubics and other things. So write EH equals CH to the CH squared, and then write EH over 2.
So in the case where we have order of age, then the relationship between how we change age and how much more accuracy we get is going to be a linear relationship.
Yes, you got it. You got it. You got it. Then if you have a higher order method, a second order method, then doubling your resolution is going to get you a way fast, way more accurate results. Okay? So the relation between the spacing and the error is going to be second order. So, yeah.
Finding this, are we integrating it? Because it's
No, we're just looking at the error. What happens to the error, the truncation error, if you have a method whose truncation error is CH squared?
No, I just mean like later, like with the whole this way integrating this.
Yeah, so we're gonna we're gonna use it in different ways. In this chapter, we're just gonna use it to calculate derivatives, but in the next chapter, we're gonna use it to convert a differential equation to a system of linear equations. Okay. All right. So if EH is CH squared, then EH over 2 is CH over 2 squared, which is CH squared over 4, but CH squared is EH, so you've cut your error by a factor of 4. Okay? Just by doubling your resolution, you've cut your error by a factor of 4. If you had a method that was first order, or order H, okay, you cut your resolution in half, or you double your resolution, then you only cut the error by half. So that justifies using higher order methods. Okay? A higher order method, such as one that is second order, there are third order, fourth order, fifth or 10th order methods all the way through, okay? Okay, now that's important because it's going to help us assess our finite differences. One last thing before you go. If you take the log of the error, log E equal log C plus P log H, and then you plot that, I'm going to ask you this activity. If you plot that on a log-log plot, so log E versus log H, then that is a straight line, right? Because that is equal y equal A naught plus PA1, okay? And this is what you get. And the slope of that line is the order. So a first order method on a log-log plot, if you plot the error versus the spacing on a log-log plot, you're going to see a straight line with a slope of 1. If you plot a second order method, the error in a second order method versus spacing, you're going to get a line with a slope of 2, okay? We'll continue on Tuesday. We'll revisit this, and good luck studying over the weekend, okay?